What's up, gamers? Okay. So, sets are going to be the first thing we deal with. Let's have a look at what a set is before we get into the nitty-gritty of what we're going to do with that bad boy. All right. So, if I have a number of sort of elements, let's say a number of numbers. If I have a few numbers, how would I put them together? What kind of data structure would I use?
Array.
Yep, an array is one sort of thing. What's another term or another similar sort of thing to an array?
A hash.
Not quite a hash. Do you guys use array as a term when doing JavaScript?
We have done that.
When you're using Ruby, do you call them arrays when you have a bunch of elements? Okay, because
Square brackets we do.
yep, square bracket boys. So the term for that is like Ruby's kind of lying to you when they call it an array. I can call them arrays here, but really I'm going to use the terms interchangeably. Lists, I'm going to say equal arrays, which would anger any type of C programmer, equals, and then like a whole bunch of stuff in square brackets. Yeah? Capiche? The difference between an array and a list is in an array, every single element in that array comes one after the other in memory, right? They have to be one after the other. But the arrays that we use in Ruby, you can like add stuff to them, you can delete stuff from them. You can't do that with arrays, so they're actually lists pretending to be arrays. Lists are ones where you can do those sorts of things with, and that's because each element points to the next element somewhere in the memory. Totally arbitrary outside of, outside of, I guess, some lower level languages, but there is a reason that people use the terms list and array differently when discussing these things sometimes. But anyway, we've got our list or whatever. Let's say we've got a few elements here. Let's say it's 2, 3, 5, 9. Also, this Kabura pen is proving to be quite confusing and difficult. Cool, that's a bit better. Or Kabura brush, I don't know. I think it's a Japanese calligraphy brush is what I was using just then. 2, 3, 5, 9. Okay, let's add another 2 here. This is a list. A set is slightly different than a list. A list has two things, or has one thing that a set doesn't, and a set has one thing a list doesn't. The thing that the list has that a set doesn't is it has an order. It doesn't have to be in order. It doesn't have to be smallest to biggest like it is here. It could be just any given order. But when you say a list, you are actually saying what order the elements of that list are in. You actually making that statement. You're like, the 3 goes here, the 2 goes here, whatever. Then here's a different one. This is a set. Now curlies, I know they mean hashes or dictionaries or whatever, or objects, depending on what language you're working in. But here, in set notation, curly brackets mean it's a set rather than a list. And so here, we'll say that we've turned this into a set. Now, this has an interesting property. It doesn't have order, first of all. I've just written it in order, but there is actually no order. If I asked you what the first element of a set is, you would say there isn't one, because there's no first element of a set. It is just a bunch of numbers. It's like, I like to imagine like a bag of numbers, right? It's not like you've put them neatly in a box or something. You've just got like a random bag of numbers jingling around. What do you immediately notice, besides the curly brackets, what's the difference between this and the list that we got from?
No repeats.
No repeats. Yeah. Like a good television broadcast, there are no repeats. We've got no repeats. Whoop. So the way to think about what a set is a set is a group of unique items. That's not actually a definition for it. I don't know any definitions for sets, but if you're thinking about a list as an ordered array of items, a set, on the other hand, is an unordered bag or group of no repeats. You're looking for what unique elements are there. And the statement that you're making with a set is you're saying 2 exists, 3 exists, 5 exists, 9 exists. So when you say turning a list into a set, this set is describing the list, right? Does that kind of make a bit of sense? Cool. All right. Now let's think about, throughout today, I'm going to use this sort of notation here. I'm going to be using sort of like, there's 2 things initially with notation. One, if this is a set A, and there's a whole lot of little things in here, A1, A2, A3, A4, A5. There's just a whole bunch of little elements in this set. This is like what we were saying previously with, if we go back, these are all these things, is like these little things here, right? Whereas this whole thing with the curly brackets is A, which is this whole big circle here, right? This is a way of sort of drawing it out, but ultimately saying the same thing. A way that you can, and this notation is sort of important because I'm going to be using it a lot when I'm writing stuff. The way that you would say that these elements are in this set, let's say we pick an element like this one, A1 here. We've decided we want to tell people that A1 is inside of A. The way we would do that is we'd write A1, we'd write this symbol, and then A. This symbol means exists in. Sorry, someone's ringing me. They can be called back. So that E is exists in. Imagine it is the E for exist. That's the way that I remember it. So you can make that statement about all of these things. You could be like A2 exists in A, A3 exists in. If we had like B2 over here, what do you think it would look like to make a statement that B2 isn't in A? Sorry? Not quite, because this isn't actually the letter E. That's how we're remembering it. Joe had a good thing to point out there. So we write it as if we're writing this, and then math is really creative in terms of how we say not. Yeah. B1 is not in A. You'll notice that I also used capital and lowercase. This is really important as well. The capital is often used to say a set, and a lowercase is usually used to say an element. Yeah? So the set is comprised of a bunch of different elements. Okay. We are ready to start to look at what we're going to look at with sets, or look at the topics. So I don't think there's much interesting about background sets. Yeah, that's just kind of what I went through here. Cool. Oh, that's another good one as well. No, we'll do that a little bit. Cool. So if we go back up here, there are 4 set notations we'll look at. They are union, intersection, difference, and symmetric difference. For those of you who were here for logic, union is very similar to or, intersection is very similar to and we'll see what we mean there in a second. And symmetric difference, which one do you think that might be from the symbol, people who were here last time? Not quite the nor, very close though. There's a different one like that.
The XOR.
Exactly. So it's the same symbol as the XOR, which, if that's total jargon, if people haven't looked at logic, that's fine. You'll have the other way around. When you go and look at logic, you might see that symbol again, and you'll be able to remember what it's meaning. So let's take 2 circles here. Let's take 2 big old circles and do ourselves a, what do we call it? Nothing mathematical about it.
Venn diagram.
Yeah, exactly. I'm not ever going to bring up Venn diagram as a term, but like it is a Venn diagram. And if you think about Venn diagrams, you can think about set notation. So we've got our A and our B, and our B has a couple of elements, B1, B2, and let's say, actually, you know what, let's actually use numbers. I'm going to say 1, 2, 3, 4, 5, 6, 7, 8. All right, there's a whole bunch of numbers here. I want you to potentially write out the set of A and the set of B. Oh, I should have asked if everyone had paper. My bad. Cool. we're getting rid of. What did I tell you?
The whole point is to pick it up by the grippy bits. You don't burn your fingers.
Ow, my fingers are burning. Look, if I had a coffee warm enough to have that effect, then maybe.
Just hot glue it on.
Maybe I should. That's probably a good solution. Or just get like an actual heat cup that isn't Garbo.
That's it. Paper.
Exactly. Save that 20 cents or whatever every time I have a coffee. We're mostly had a crack at this. Is there anyone who still needs a bit more time? Nope. Okay. In that case, what do we think goes in A? I'm going to have to rewrite a bit of this because I'm not giving myself enough room here. 3, 2, 8. 3, 4, 5, 6. Oh, actually, it is 3 to 8. That's wild. Cool. It's going to save me a bit of time. Is this better now? Yeah, cool. This will actually erase stuff. All right. So I'm just going to write 3, 4, 5, 6, 7, 8. At this stage, you do have to write all the numbers out, but we'll look at a way of writing less in a second. We don't have to worry about as much then. How about B? 1 to 4. Whoa. There we go. That's a bit more legible. Cool. So that's exactly right. So these elements in the middle are in both, aren't they? Yeah. Let's look at the sort of terms we had here: union, intersection, difference, and symmetric difference. What bit do you think this middle bit would be? What do you think that would be called? Oh, I don't like that color. It's too dark. There we go. This bit here. So we've got union, intersection, difference, and symmetric difference. Okay. Hands up for union. Hands up for intersection. Hands up for difference. Hands up for symmetric difference. Okay. As voted by democracy, math has now decided this will be the intersection. Also, it is actually the intersection, so don't you worry. So if I was to write it out, we've looked back at this document here, the textbook, and we'll see we've got this little symbol, which we call a cap. So we've got the cup and we've got the cap. And you'll notice it's U for union and N for intersection. That's how you can remember it. So we've got the intersection there. So we can write it as A intersection B. And that would be our 4 and our 3. Yep. Does it matter that I wrote 4 first?
No.
Why not?
Because I don't know what.
Sets don't have an order. Wonderful. So that, if the N is the intersection, then this is going to take a little bit of speculation on your part, except for those who've already done it. What do you think the union will be? We haven't explored union yet, but we've looked at the intersection, and you might be able to guess that, if the intersection is one thing, the union is going to be a different thing. That will probably be along the same kind of lines of thought.
Numbers outside?
Sorry?
Just the numbers in each one?
Write that down. I'm going to get everyone to have a crack at it, and then we're going to discuss which one will be.
Do we have access to that page?
This page? Yep, it's in the textbook, but I think is in the Slack. And it should be pinned as well. If it's not pinned, I'll drop it in there and pin it again. And also it'll be in Canvas, I think. No, it won't be in Canvas yet, for some reason. Because I'm battling with Canvas. And I'm losing. Rails is battling with Canvas? Or you're battling with Rails?
I'm battling with Rails.
Oh, okay.
And losing.
Oh. Look. It's a worthy opponent.
Well,
If it was an easy victory, you wouldn't.
Not winning.
Sorry. It's a war of attrition.
People having a bit of stalemate and it's starting to
had a bit of a crack at this point. So what elements do we think will be in the union? And you can just describe to me, you don't have to say the individual numbers out, I'll still write up the numbers, but what bits will be in the union? This side of the room?
1, 2, 5 to
1 to, what? 1 to 2, 1, 2, and then 5 to 8? Okay, so not the intersection.
I think it includes everything.
You think it includes everything? So hands up doesn't include the intersection? Hands up includes the intersection.
And the rest of it.
Yep, and the rest of it. Okay, wow, that's pretty even. It does include everything. The union is all things. It's all things coming together.
The Brady Bunch.
Yep, the union, yep, it is the Brady Bunch. Look, I'm just going to write it like this because I can't be bothered to write all the numbers. But you can't do that because when you do the test, you have to type it. So, haha. Okay, so that's our union.
You drew the picture and coloured it in, okay.
Yeah, that's all I did. I drew a picture and coloured it in. And as you can probably tell, I may have failed kindergarten because I wasn't able to stay within the lines when I was colouring in. All right. So what was described by a couple of team doesn't include the middle, which is a long team name, and I don't expect to see you at trivia. Sorry? Yeah. So, yeah. Which one do you think it is there? The difference or the symmetric difference?
For everything except for the middle.
Except for the middle?
Difference.
Okay, so let's have a look at what difference is. I'll write out difference. I'll write out difference as a sentence, or as a sort of mathematical way of looking at it. Cool. I'm going to do it on the side. If I did a... Why is it going so faint all of a sudden? Keep having to go back. If I went A minus B, that's difference. That's like a subtraction. What elements do you think are going to be in A minus B? Do you think that A minus B is going to be the same as B minus A?
You mean the same answer?
As in, yeah, do you think that these are both going to have the same answer?
Not if you passed kindergarten, I don't.
I mean, there's a lot of things there are a lot of things in sets where it doesn't matter which order you do the operation in,
And the subtraction is not one.
That's
and subtraction is not one of them. Yeah. So A minus B, first of all, what do you think A minus B is?
Everything in A minus everything in B.
Which leaves us with,
5, 6, 7, 8.
yeah, 5, 6, 7, 8. What?
What?
B minus A leaves us with 1, 2. That was incredible. Okay, what if we did A minus B? Well, that's wonky as hell. A minus B union B minus A. What would we end up with?
Not the intersection.
Everything but the intersection. So A union B minus A. Whoa, why did I say A and write a B? A intersection B. Those two things are saying the same thing, right? You're saying subtract B from A and then add it to subtract A from B. But you end up with the outside bits here. You end up with these two, but you don't end up with this thing. And the same is if you go A union B, which is everything, and then you subtract this middle bit here, you end up with the same thing. These are both the same. Which is also, this is something to remember, also ends up being the same as A symmetric difference B. So notice we have the difference of, difference is A minus B or B minus A. Symmetric difference is a difference but in both directions. Yeah? Cool. Alright. Now, how else can we do this? What else should we look at? We've looked at union, intersection difference, and symmetric difference. Let's have a look at did you still want some time to copy any of this down? I mean, this is all going to be recorded, and I can also just dump the canvas in the Slack as well at the end, if I remember to save it.
The symmetric difference, just to clarify, is just everything that they don't share.
Yes. Everything not in common between the two sets.
So if A and B did not overlap at all, it would just be the same as A union B.
If they didn't, yeah, exactly. Yep, and if they overlapped entirely,
It would be an empty nil null set.
Yep, exactly. Cool. I don't think we have to worry about complement, do we? No, we do have to worry about complement. Sorry?
That just makes it opposite of, doesn't it?
Complement?
Yeah.
Yeah, exactly. Cool. All right. Let's continue then. I'm going to give you S is going to be this is what I can do better than wait. Okay. Oh no, I'm going to do it as a string because you know how let's say we're turning a set of a string. Let's do that, which means that we're looking for each individual and unique element in that string. Yeah? We're happy with that? The string is going to be he's okay. And then we're going to have the second set, which is going to be T. Wait, that's not it. I can't remember.
Oh, you're going to do the she's not. Okay.
Yeah, I was going to do the SBev. What is it? Oh, she believed? Is that it? Yeah, there we go. Cool.
He lied.
Is it he lied?
He lied.
Oh, she believed. Okay. She believed.
He lied.
All right. And then T is set of he lied. Okay, find S minus T. Actually, I'm going to find S minus T first of all.
So just to clarify,
Yeah.
each character counts as a separate entity in that.
Yeah.
Well, here's the issue.
I've never done it with strings.
Yeah. So if this was an array, because we're treating strings like an array here,
Yeah.
that means that you're actually only going to have like one E, for example,
Okay.
because the E is a unique element that only occurs once. So if you actually typed in, let's say you went into Python, you wrote set and then put brackets around a string, it would legitimately tell you one of each occurrence of each letter.
Mm-hmm.
Yep.
Are capitals and lowercase different things? And is that a capital S?
Ooh, yeah, it is. It is capital S, and it's the only capital there, so you only have to think about it once.
In general, though, it would be different, wouldn't it?
Yes, I think so. I'm not going to give you a whole lot of strings to do set stuff with, though. This is just me having a bit of fun.
If you had a string, comma, another string,
Mm-hmm.
would we still treat every character as an individual there, or is it that string and that string as the individuals? Like, can you have a set of strings?
You could have a set of strings. Yeah. If you think about it like the same way you handle lists in like Ruby. If you had an array or a list of strings, it would treat each string like an element. But if you had a single string, it would treat each character as a element in a list.
Well, if I had an array and just put hello in it, it would treat that as one.
Yes.
But
if you had hello, it would treat that like an array.
If I went .char.
Really? Is that how Ruby handles strings?
Yeah, if I only put hello in the array, that would just be position 0. I can still
Wait.
access each character separately, but it's not an array.
Word equals hello. Oh wait, I'm not in IRB. Wait, I don't have IRB installed. Okay.
I can still do what you're saying. Like if I said right now, word 0, I would get H.
Yep.
But hello is not in an array. Word is just a variable.
If hello was in an array, then it would be the first element of that array.
Yeah.
Yep.
Like the whole word would be, not
Yes.
just a separate.
We're in agreement here.
I can't remember what I was asking. But
Yep.
like, so if I had hello, she believes.
Yep. Separated as an array.
Yeah.
Yep.
So that's 3 elements in the array.
Exactly.
It's going to treat each word, not each character as a change.
Yes. Okay. Cool. All right. We're on board. You've got an answer ready? S. Wait. S. Yeah. B. V. Yep. Yep. So we subtracted T from S. We end up with SBV because E is in both of them. Cool. So it's not even SB, which is the bait and switch that I did with a few people. But I told you guys that we can't really double up on the E's. Radical. Okay. How about let's find the symmetric difference between these two. Yep. That was the one that's like round the outside. You know, I got a bad review for this course from like 2 people anonymously because I made too many references.
Too many references to what?
Just like they said pop culture. The review said discrete math was okay, but he made too many references to pop culture. I don't know who it is.
I love references.
But they're now my least favorite student.
References are good.
I hate when the space counts, doesn't it? As a character.
Ooh, yeah, wouldn't it?
Especially this one.
Same thing. You know, for symmetric, would it be the one that we crossed out? Should we cross out?
All the ones that we crossed out? What do you mean crossed out?
No, well, that one.
Yeah, it says ones that are in common.
So, would the one on the bottom be?
Symmetric difference would be everything except the ones that are in common.
Okay, so.
So if it's in both of them, then sort of. I wouldn't say it that way. I wouldn't want to quite go down that path. Think of it as if you were to cross out ones that had in common, it'd be all the ones you were allowed to do. But you had to cross them out on both sides. Right? Yep.
The ones that we crossed out on both sides are the ones that inside was
The middle.
Oh, you
Bit inside the intersection.
everything
Which is
except
part
the
that's
in common.
the part they have that's the same as the intersection. So I'll do it that way actually.
Because T has nothing in it, and they share.
Yeah. Yeah. Yep.
So pretty much S minus T is the same thing as S.
Only in
All
this
case.
all the time.
Yeah,
Yes,
only
okay.
No, no,
Yes.
Yeah.
normally,
Only-
S thing OT is just everything except what they have in common.
Only
In this
because
case,
all the
T
bottom
is
values-
quite entirely in common with S.
So, all right, we're going to go through this one. People. Okay, so this one, if we write this out as a set, then we have S H E B L I V D, right? And a space. Yep, sure. Let's put the space in there as well. This one we would have H E L D and a space. Thank you. Now, if we were to cross out the ones they had in common, we'd be like bang, 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 bang. Wait, I? Is there an I in the bottom one? Yeah, there is. My bad. There you are. Cool, 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 cool. So all we're left with is actually only elements from this set. So it's actually, in this case, it is also SBV. So these are the same in this case. That's not always true, though. And I probably should have used an example where it wasn't true. So we'll do another one. Another one. Okay. Yep. Or we'll come up with a more interesting example to use for the other one. Let's have a look at what the examples I used here. If I can hyperlink to that. Okay, fine. Wait. No, okay, fine. Oh, also, the textbook has, like, this thing, which is nice.
The line above is not, isn't it?
Yeah. So that's just not the intersection, which is the same as saying the O plus thingy. Symmetric difference. Okay, there's not really a great example here. Okay, damn. Well, I guess it's back to... Ooh! Here's how we'll do it. Alright. Like, you know, new notation way of doing things. X given... Ooh, that's new. X is greater than or equal to 0, and x is divisible by 2. Yep, and I'm going to just point out this notation here. Divisible by
A slash
2.
or is that?
It's a pipe, but it's a smaller pipe. Maybe I could say, or I could say if you want x mod 2, or x percentage for x mod 2 equals 0. Is another way you could write that out. But let's divisible by 2, okay? This is a big old pipe. So like, you know, the pipe key, like the vertical line. So this statement is like shorthand. So remember before when I was saying you have to write 5, 6, 7, 8 out? You can actually write for that, you could write x, where x is greater than or equal to 5 and less than 8, and it's an integer. Yeah? But now we've got this for x. Cool. X where x is less than or equal to 0, and x is divisible by 2. And actually we probably want to set an upper limit as well, because otherwise that's every even number bigger than 0, which is quite a lot of them. So let's say x is less than 10 is the last one as well. Now we've got a second set, which is set y. So this is set x. Got a set that's set y. Y given y no, there's not a lot I can think of that's not going to be almost identical to this. Y is greater than 5 and less than, greater than 5, and y is less than 8. Yep. Less than or equal to 8. Next question is x o plus y equals what numbers? And you can write it out this way if you want to, or you can write out the individual elements. This notation I know has suddenly got a bit crazy, but at the same time, all you're doing is you're breaking it up into individual bits like this, separated by semicolons, and just come up with rules. So it's sort of like if statements or something in code. Think of this as a for loop, is one of the better ways to think of it. You're looping through all these numbers, and this is just declaring the variable that's going on the loop, and you're setting what happens to it. Dot back for 1 second. They'll come back. Cool. You're good? You're almost good? You're good?
I am.
You're not good? Alright. Just give me a moment then. I'm going to go with my notation as well.
Oh, right.
Yeah, what's good?
Hey?
Yeah, you guys know you do have to pass this test, right? Like, okay. What is it? Oh, okay.
It's not a good excuse for that one.
I
Yeah. Oh, you did say that. Oh, God, I did say that. I thought you could free fire on highlight stuff. See that?
should we work our way through it now, or do people want like another minute or two, or another like not minute but like crack on, crack away. All right. So if we had to evaluate in quotation marks this expression and work out what was there, let's do that first. Let's say what would it actually be? What is this saying? So this is saying from 0, so 0 all the way up to 9, but divisible by 2. So would 1 be there? No. 0, 2. Is 0 greater than or equal to 0?
Yes, but it's not divisible by 2. You can't say 0 divided by a number.
Okay, how about here's a trick. 10. 10 is that divisible by 2?
Yes.
Yeah.
But it's not in there because
You
it's
can't
saying
divide
X
by
less than
0, but you can divide 0 by a number.
Yep.
If I had no pens and we could share them all together, we'd all get no pens. You got that same.
I thought you can't divide by 0 or get divided by 0.
Here we go.
By 0, I can't share
Are you ready?
5 pens between no people.
Are you ready for this wild journey? Yeah.
Why is 0.0?
Because since it's an integer getting divided by something that doesn't just fit into
Zero
it,
Python.
it turns it into a float. Yeah. Yeah.
Getting those war flashbacks.
Yes.
Okay. 2, 4, 6, 8. Is 10 included? No, because it's less than 10. So that's not a comma. All right, how about this one? So y is greater than 5. What are we starting at? 6. Not 8?
Wait, no, don't worry. I looked wrong.
It also just looks like I wrote it badly, so I can understand. So what is the symmetric difference between these two?
0, 2, 4, 7.
0, 2, 4, 7. How do we get to that? Well, if we look back at the previous ones, is 0 in both of them? No. Is 2 in both of them? No. Is 4? No. 6? Yep. 8? Yep. So what would the union be if we were just to ask what the union is of these two sets?
All the numbers?
Oh, sorry. Yeah, the union would be all the numbers. What would the intersection be? Sorry.
6, 7, 8. I mean, sorry. 6, 8.
Yeah, exactly. It would just be 6 and 8, which are the two we've scratched out. Because the 6 and the 8, like the intersection is exactly the opposite of the symmetric difference. Cool. All right. So we're left with 0, 2, 4, 7, 8. Oh, 7, not 8. Scratch that. 0, 2, 4, 7. Wunderbar. All right. What else have we got to look at? We'll look at two last things, and then we'll take a bit of a maybe like a 10-minute break, 15-minute break or something. Okay. So pretend that we've got I'm going to call this a space, right? This is saying like there's a whole bunch of stuff here. These are all going to. There's going to be numbers everywhere. There's ones. There's threes. There's fives. There's 26s. There's all these crazy numbers, and then we've got a set A, and we've got a set B, and there's maybe there's 4, and there's 32, and there's -6 because we can have negatives if we're talking about integers. And there's, give me a number, 12, and there's 40. Okay, so we've got all these numbers here, right? The space could be, it could be all sorts of things. We could have just said what numbers are in the space, or we could say, it's all even numbers is the space, which can't be because there's a -6 somewhere in there. The space in some ways is a lot like a set, but we're not really talking about the space that much. If I said A minus B, right, what would you tell me? Yeah. A minus B would be a set of 12 and 32, because it would be this minus B, which includes the -6. Yep. What about if I told you, what if I asked you to find the complement of A? Now this, the complement, so the complement means everything, everything that isn't A. This is a bit of a weird one.
-6 does count with them.
Is -6 not in A?
It is what something B.
Yeah, but we're asking for all the things that are specifically just not in A.
So everything.
If you went into a clothing store and they're like, here are all the clothes, and you said, I will buy everything, but I don't want anything in green. Just like, give me everything except the stuff that's in green. Or if you were, that's probably a better example, is like with if you're eating a pack of snakes or something, like, I don't like the green ones. I'll eat all the ones except the green ones. I don't know what my vendetta is against green today, but it begins now. Cool, so the complement of A. You don't have to write them all out, you can just tell me if you want.
All the numbers there except 12 and 32.
Yes. But when you say all the numbers, what numbers are included?
And not -6 either, sorry.
Yep. So this also is the 1 and the 3 and the 5 and the 26, because even though they're not in either of the sets, they are not in A. And that's where this becomes important, right? Yeah. This also would be, if we did something like, if we wrote something like, another way of thinking about sets and not having to worry about spaces and all that weird jazz, is if we wrote A, here's our circle, B, and then we wrote maybe a third one, C. We're not going to go too wild, too many circles here, but let's say 1, 2, 3, 4, 5, 6, 7, right? That's a whole bunch of numbers. What would the complement of B be here? We haven't declared our space, so just assume that this is all there is.
1, 3, 7.
1, 3, 7. 1, 3, 7. Yep, that's cool. That's right. So you're getting a bit of an idea of what the complement is then, which is good. So I don't think we need to go into complement anymore. Actually, let's do one last thing. Let's do one last thing with complement. Let's do one last thing with symbols in complement. There's a few symbols that are special. There are a few symbols that mean really magical things. Like, for example, N. The letter N. Which means natural numbers, correct?
Means 1 and up. Hold on.
As long as they're not.
Or hang on, I think 0 and up.
0 now?
Yep, 0 is included. Oh, actually, this is really funny. I had like marking confusion from the campuses. Oh no, actually no, it's just from us. About some people including 0. I had to read into it. It's actually still a point of debate. As in, even when you read into it, people still argue over whether 0 is a natural number or whether it's a real number. Yeah.
So,
Real numbers include negatives.
Yep.
Natural numbers are all positives.
Yeah.
Whole numbers.
but
Integers are all positive and negative whole numbers.
right.
Yep.
It's a whole bunch of fun.
Yeah.
So natural numbers is, let's for the purpose of this, and I won't mark you if you have strong feelings about where O should lie, where O should lie.
So this class
But let's
is
say-
counting 0 or not.
It doesn't matter. I don't care. You can count it all you want. You don't have to count if you don't want to. I'm not going to take. I'm not going to come.
In our exam, do we count it or not?
look, I'm keeping this lesson apolitical. I will mark you correct whether or not you include A as a, yeah. Yeah, okay, I'm not taking sides here. I only do that with actual politics. Okay, so we've got greater than or equal to 0. Let's say that. Or like not. Who cares? Because I'm going to mark you right based on whether or not that's there. Hell, even have a... I'm going to invent a new symbol here. It's going to be a maybe greater than or equal to. There we go. Wow. I'm going to call this... I'm going to name this symbol James's uncertainty. Yeah. Okay, cool. So we've got our natural numbers. We've got our integers. Those are probably the most important ones. I'm not really going to ask a question about any other ones. Maybe F for pay respects. But like these are the two main ones, right? There's a whole bunch of other ones as well if we really got into it, but we're not going to. If I asked you, if I said, here we have a set of X where X is in N, what do you think I'd be saying?
You can say whole number above the 0 or above.
Yeah. So it's all, you're just saying all natural numbers then. That's what the statement is. That you would have a set, and that set is the same as N, because it's just all numbers in N, all natural numbers, or can be all natural numbers. How about if I asked for this set?
Oh, it's not so it's any other
It's
number.
negative. Oh, well,
No,
it could be negative or it could be a decimal.
Yeah, it could be like 3.9. It would be enormous. In fact, I think it would be an infinite set. This would actually be the same as if we said X in N. That's
Actually, considering that the natural numbers are positive, 0 would not count.
But 0 isn't.
this is the problem. This is why it's a debate.
Because 0 isn't positive or negative.
Joe,
You
I'm
can
gonna-
approach 0 from the positive side, but 0 is neither.
I'm going to need you to look at up-to-date 2019 maths, which includes James's uncertainty principle with the presence of 0 in not in. Sorry,
Use that in
it is now. All right, so X
It's like
is.
saying 1's not prime. Like technically it comes under the thing, but it's not really.
Let's not go there. I legitimately read a very long back and forth between two mathematicians on a forum about this because I was trying to come down on one side or another.
Which one confused? Which one did you believe more?
Which one did I believe more?
Exists.
No, the only answer that I agreed with was the one that was like you can't say for sure. All right, cool. Enough fun. Back to serious. That's what I'm trying to say here. Is that the x is all x's that are not in n is the same as saying the complement of x's where they're all in n. Oh god, that notation isn't correct because we're missing an x there. But do you get kind of what I mean here? X, where x is in n. The complement of that set is the same as the set that is everything else. Don't worry about stuff that kind of like crazy
That's
too
the
much.
same as saying X is not a subset of N.
Yes. Oh yeah, let's look into subsets. That's the last thing as well. And then the 10-minute break. Subsets. Okay, so this is big A
So was the little c above the n then, or above the whole set?
above the whole set. So the complement is something we say about a set, not about an element of a set. Yeah. But you could say, because n is a set, you could say n complement. In fact, we could say, yeah, you could also say, here's another way of writing it, you could also say x in x, where x is in n complement. Yeah, that'd be fine as well. There's just a lot of different ways of writing this. Cool, but let's look at this. We've got a big A here. We've got B hanging out here, right? 1, 2, 3, 4. What can we say about B? What's the statement we can make here? There's a certain statement that I think Joe just said, but I'm going to touch on it briefly. Yeah. So there's a symbol that looks like this. It's like that. So it's a very stretchy seat, or like a wave or something. And this is called a subset. Set. Ooh, subset. Wow. So subset. So is A a subset of B or is B a subset of A? B is a subset of A. Okay, cool. I'm happy with that. What about, and here's a radical thing here. This is truly mental. What if we drew this circle? What if we drew this circle, but better, and called it C? Right? Which sets are a subset of B?
Nothing's a subset of B.
No, it concludes all the elements of B. It's just badly drawn. That's all.
Yeah, but C is still not a subset because it's bigger than B.
Okay, so what are subsets of C?
Oh, A and B.
A and B?
No, C is a subset of A.
Yeah, so
C is a
C's a subset of A and A is a subset of B.
Yeah. Okay. So here's the part that's really messy. So B is a subset of C. We are happy with that. So B, we know that for sure. B is a subset of C, and B is a subset of A.
And C is a subset of A.
C is a subset of A, but it includes all the same elements as A, right?
Yes.
A is a subset of C.
Wow.
This is weird. Subsets can be the same thing. But generally, we don't like that. So, I don't mind. There's a whole thing about proper and improper subsets that we're not going to get into. We're mainly going to focus on these sorts of subsets, which are called proper subsets. These ones, you actually put a little symbol underneath here as well, like a greater than or equals to, because it can be the same set. But we're not going to stress out about those ones. I just kind of wanted to go there for the sake of it, just to make you guys aware. That's the main one we're looking at, which is a proper subset. Yeah? Capiche? Cool. I will go back to that so you will be able to have a look at it again in a second. Oh no, not source mode. Cool. Ready for source. Was there anything else here? No, those ones are fine. We've done that. We've done this. We've done that. Well, way too much me. Any questions before we take a little bit of a break? Yeah, okay. Alright. Yeah, okay, cool. Let's take a 10-minute break then, and we will come back and we'll look at O notation. Get yourself